Hi everyone, and welcome back to JTAG YouTube channel. In this episode we'll try to have a look and fix this Commodore 16 that I have since more than 10 years now. And this is the dark side of the Commodore, as I like to call it, because this line of computers has this dark color. And also another dark thing about this one is just a black screen, which is a common fault. Actually, I know what it is, because a few years ago I've received some other members of this family, so I could swap a working CPU on this one, and this one started, so I know what it is. This line of machines has the infamous 8501 CPU, or very early 7501, which was the HMOS1 version of this CPU, which is instead fabricated with HMOS2 process. Anyway, this CPU is really famous to go bad, and when I substituted a good CPU on this machine, the machine seemed to work fine. So what can do in this case is find another working 8501 or 7501, which is very expensive at the moment. There is a project to substitute this one with the 6510, which is the Commodore 64 CPU. But this requires to change the kernel ROM, because the 6510 is not really compatible with this one. We'll see later the differences. Also, the 6510 lacks one of these input pins of this CPU, and that seems not make any difference on this machine. Didn't see any report of crashing or something, but I'm sure Commodore made a new CPU for a reason. So what I want to understand is how this machine works exactly, and if we can replace the CPU with a 6502, which is the core inside the CPU, plus some other logic. I have a good feelings. The process will be quite long to design something to allow a 6502 to work in this machine, but let's see what happens. This is the first page of a very preliminary datasheet of the MOS7501. It is so preliminary that this still reports the manufacturing process as NMOS, when in fact the 7501 was produced with the HMOS process. The description says the internal processor architecture is identical to the MOS technology 6502, and this is good news. Then, the CPU has a 7-bit bidirectional I/O port on chip with its data direction and input-output registers located at the first two memory addresses. Also, the CPU has an additional control pin called AEC that can put the CPU address lines into high impedance state, also known as 3-state, to allow easy DMA operations with other devices taking control of the memory bus. So far, it seems just a slightly different 6510 CPU, the famous C64 But if we compare the pinouts, we see some noteworthy differences. The 6510 has only 6 I/O port bits from P0 to P5, and instead the 7501 has 7 bits and only P5 is not present. The second and most important difference is the signal called gate-in on pin 23 of the 7501 that doesn't exist on the 7510. Of course, to add 2 extra functions on the already full 40-pin AC case, they needed to sacrifice 2 other functions, and the choice was to eliminate the phase 2 output clock that can be reconstructed with external logic, and the not maskable interrupt input, which is the NMI pin. Now, most of the CPUs on the TED-based machines are actually marked as 8501. The 7501 was manufactured with the HMOS1 process, and the 8501 with the HMOS2 process. Now, how to implement the missing parts? I have a very good understanding of the I/O port and the AEC signal mechanism, as they are exactly the same as implemented on the 6510 CPU used on the C64. But what exactly gate-in does? I have never had any working TED machine, not for long enough anyway, to gain some good knowledge about it. The preliminary datasheet has no description of this signal. The TED architecture manual reports this explanation. Gate-in control line is provided to hold off the read-write line until raw address select makes the transition from low to high. This prevents the read line from making an early transition to the write state, which would cause an improper early write cycle to occur. It still doesn't make much sense to me. In the C16 computer, the gate-in input is tied to the TED max output that controls the dynamic RAM address multiplexer, so indeed it has something to do with the DRAM accesses. But why it was not needed in a C64? Why a 6510 CPU has no issue with this improper early write? And why a 6510 can still work in apparently fine in a C16? As I often do when I'm in doubt, I started a thread on CBM hackers mailing list. But I've also decided to start the project anyway, since this gate-in input seems not to be essential for a C16 to work properly. Since I want this project to fit in a very small footprint, I can't use discrete logic chips. There would be needed too many of them to fit in a deep 40 footprint. Also, FPGAs are out of question because of the 5V requirement. What remains is the CPLD kind of logic chips. However, the only chip that fits inside a deep 40 footprint is a 44 pins TQFP, and it's really tight fit anyway. The problem is that a simple 44 pins and 32 macrocells CPLD isn't going to be enough for all the logic function required. But here's the crazy idea. Let's use 2 CPLDs instead of 1. Maybe I can divide the logic function into sets that can fit on 2 separate 32 macrocell CPLDs. So I started the crazy design on KiCad and also downloaded all design software from the Atmel, now owned by Microchip Technology site. Fortunately, the old school CPLDs are still in production in 2020 and are really inexpensive too. The process of designing custom logic into CPLDs requires to tentatively assign functions to pins, trying to have the easiest possible trace routing, and at the same time trying to compile the logic into the CPLD design tool to see if it fits correctly with the assigned pinout. Sometimes the compiler can't fit the logic design with our chosen pinout, so it tries to come up with a different pinout that can be very different from our preferred one. I learned to accept some suggestions and swap some of the special purpose pins that are the ones that matter most anyway, and then try to stick with all the other preferred assignments for routing constraints. After a few trial and errors, I could complete the routing and have the compiler fit the design with the required pinout. At this point, it's time to run the logic simulator software that allows to verify that the signal really do what I wanted them to do. By the way, one CPLD is only doing the address bus 3-state function and handling the AC signal, and the other is implementing the I/O port and the gate-in function, or at least that's what I hope. After a quick check that I have enough clearance between adjacent pads and that so the mask areas don't overlap, I decided to order a small batch of PCB to make the first prototype. However, shortly after ordering the PCBs, finally I understood what gate-in is for and how it's supposed to work. A member of CBM Hackers sent me some scope traces. The problem arises from the fact that on TED machines the CPU can be clocked at two different speeds. The slow speed is about 1 MHz, and this clock speed is used whenever the TED chip needs to draw the screen and refresh the dynamic RAM. In this code capture we have the read-write line in yellow, the CPU clock in light blue, and the purple trace is gate-in signal that is in fact derived by the MUX signal from the TED. This signal makes a full DRAM access when it pulses high then low. Notice that max high phase is approximately 200 nanoseconds wide and the low phase is approximately 300 nanoseconds wide. Now let's observe what happens when the CPU is getting the fast clock, which is twice as fast as the slow one. Yellow is always the read-write line, light blue is the CPU clock, and purple is the max that drives the gate in. Now, max high phase is still the old 200 nanoseconds and the low phase is still 300 nanoseconds. Also observe that the read-write low pulse is wider than the high phase of the CPU clock. This can happen on a regular 6502 or even on a 6510. What's going on here? Turns out that Commodore wanted to use 200 nanosecond RAM chips, so the only way to meet this requirement was probably to always access the RAM with a slow cycle even when the CPU is running at twice the clock speed. To obtain this slow cycle, read-write line must be held fixed for an interval longer than the CPU clock high phase, and this is why gate-in was born. So my newly born design is broken, but it should still work as much as a 6510 based replacement, since even the 6510 can cope with this slow down memory access. It happens to work fine since not all TED machines were born with the 200 nanoseconds dynamic RAM, but often with much faster ones, like these 150 nanoseconds DRAM chips inside my C16. Also, the real 200 nanoseconds dynamic RAMs can usually tolerate some faster access anyway. If you have a TED machine with a 6510 CPU replacement and you experience random problems, please let me know in the comment section. Can I fix my design by making a new configuration to the CPLD that's handling gate-in? Unfortunately, I can't, since that one is fully utilized and I don't have any other resource left. What I will do in the revised design is move some function to the other CPLD that still has plenty of resources free. However, this means I have to reroute a few signals and make a new PCB. So, the prototype PCB arrived, and here's one sample. So now I have all the components to make a prototype of the first revision, which, as I said, is not working correctly, but it should emulate the same behavior that happens when you substitute a 7501 with a 6510. So it should work enough to prove I'm on the right, at least on the right path, so I can change the design enough to make a real 7501 emulation. So I will show the actual bidding process. There are plenty of tutorials to make some SMD assembly work. This one is a bit tricky because of the very little clearance between the socket pins and the CPLD, but I'm confident I can do that. Well, anyway, I'll try. So once it's assembled and programmed, I will of course show if it works or not in the Commodore 16. Now, before soldering the socket and the pin strips, I wanted to confirm that I can program both CPLDs correctly. I've made a simple JTAG interface for the old PC parallel port, following this schematic. There was no space to have standard headers, so I've just made a few small pads to solder the wires needed for programming. Then, I am an hardcore Linux user, so I wanted to confirm I can program these parts using an open source JTAG software. But before this, I need to convert the JTAG files to the SVF format using the Atmel programming tool under the Wine emulator. Of course, everybody else could use the Atmel software on a real Windows PC with any parallel or USB JTAG interface. Finally, after finding and eliminating a solder bridge I had unintentionally made on my homemade programmer, I could successfully program both CPLDs. Now the day arrived, finally we'll test this replacement with the 6502A, the 2 MHz version, with my replacement board in the Commodore 16. Also notice is much higher than the original chip. Let's compare the height. Well, much higher, but it has the same footprint, of course, that's by design, and also the shield open to close fine, so it seems there are no problems about this. But will it work? Let's power on. So a moment of truth. Woohoo! Wow, that's something, really something. Okay, video quality doesn't seem too much good, but byte count is good. Commodore Basic. Now I'll try to connect to the keyboard. I don't know if it's this monitor or something like that. Yeah, I will try the input to my tuner card and see if it's better. But yeah, it boots. It's still alive. And as I said, this prototype has the bug, the same problem that has a 6510 replacement. Only this one doesn't need any kernel replacement or anything. So it seems it was not so easy. The machine is a bit too marginal when using the disk drive. It appears to work, but sometimes it hangs. I don't know if it's this. Yeah, you see, device not present at the moment. It is a 1571. But yeah, there must be something wrong. I don't know, I need to troubleshoot this machine further. It may have other issues because it's really the first time I happened to use this machine. I have no other TED based computer, so I cannot swap parts. So I really have to troubleshoot the whole machine without any possibility to swap parts. Maybe a corrupted disk, but well, it loads fine. And thank you for watching.